Our lecture today will deal with the computation of more transfer functions and their representation in the frequency domain via the use of Bode plots. There are a number of rules that apply to the drawing of Bode plots that you need to know, and that we will do by means of examples. First, I would like to bring the transfer function h of s, so h of s is equal to 1 over s. The Bode plot, as we have seen it, summarizes as follows. The size of h written in dB versus omega, when we plot, of course, h of j omega. So omega looks like a line of negative slope -1 when we represent h in decibels and omega in decibels as well. And it crosses the 0 dB line at omega is equal to 1 radian per second. Now the phase of h, we know, is equal to steadily -90 degrees. And so let's see how this plot works in the machine world. So you probably remember that we define our transfer function as h is equal to 1 divided by s. Then we define our system is equal to syslin of continuous time comma h, so that we can then plot Bode of sys. When you look at this plot, you notice one thing, okay? And that one thing is that we don't really see, well, actually, I guess we do see this 1:1 slope. However, what we see is that the gain crosses the 0 dB line at another number than 0 or than 1 radian per second. And in fact, what it is 1 radian per second. However, you see that the frequency here is not plotted as in radians per second, but instead in hertz. So what does that mean? Well, when I multiply a frequency, say 1 hertz by 10, I get 10 hertz. When I multiply it again by 10, I get 100 hertz. So this spacing here between two successive frequencies or two orders of magnitudes of frequencies here still correspond to a decade. Okay, and so what we see is that for that transfer function 1 over s, the size of 1 over j omega, the size of h from one value to the next decade, indeed decreases by 20 dBs. Okay, so for example, here it was at 0 dB, a decade later it is minus 20 dB, and then a decade later it is minus 40 dBs. Okay, So the slope of this thing is indeed a slope that we can call -1, since a factor 10 here corresponds indeed to 20 dBs. And so the line here decays by 20 dBs when this guy goes up by 20 dBs. So that's a -1 slope. The problem has to do with the so-called crossover frequency, the frequency at which this guy crosses over the 0 dB line. And that happens at 1 radians per second, but 1 radians per second is indeed a little bit bigger than 10 to the -1 hertz, or 0.1 hertz. So that can be a little bit of incommodating. And so it turns out that this is sort of a peculiarity of Scilab, which is not present in MATLAB. One way of going around this peculiarity is to do the following. What you do is instead of plotting the body plot of the system, what we're going to do is we do a change in the frequencies. Okay, we define S is equal to S divided by 2 divided by pi. And what we get is the scaling effect does exactly what we want. That is, if we define now H as 1 over S, after having defined S this way, we obtain kind of a strange H because of this 0.159 factor. But this 0.159 factor is exactly a factor 2 pi that we need. Because when I define my system as the system corresponding to that transfer function, which is in fact 1 over S, not 1 over this guy. Okay, let's see what happens. Okay, we write this. Okay, and then sorry, my mistake. And then we can plot body of cis. Here's what we get. You see, we get the same effect as if instead of measuring this in hertz, we replace those numbers by saying they are in fact in radians. Okay, so you forget about the hertz, you read this thing as if they were radians, and now at 1 radian per second, we get exactly a gain of 1, meaning that 1 over 1 radian per second, which is the magnitude of the transfer function, is exactly what we want. Okay, and the slope here remains a slope of -1. So again, if you use this little trick of redefining S that way before defining your transfer function, then when you compute the plot of that transfer function, you read it exactly as if these numbers were in fact radians. And so what you do is forget about that frequency in hertz, and you replace it by frequency in radians without changing any of those numbers, and you get exactly what's needed. Okay, and here of course we get the phase, which is -90 degrees and constant. Okay, so let's go back to computing a few interesting transfer functions. Okay, well, the purpose of all these lectures being, of course, to help you learn how to draw these transfer functions. So once we have 1 over S, we can do, for example, 1 over S squared. Why is that? Well, 1 over S squared is just, so first of all, the transfer function we want to plot is 1 over j omega squared, right? This is h of j omega. Now we know this is just 1 minus 1 over omega squared. Okay. But there is and we could go about plotting this. Okay. We can go about saying the following. Okay, 1 over S squared is really 1 over S times 1 over S. And so what does that do? Well, when we compute the phase of any particular number A, okay, it turns out that the phase of A squared is just 2 times the phase of A. For example, the phase of J is 90 degrees. The phase of J squared is the phase of -1, which is equal to 180 degrees. Okay? So you have these things here that happen. So what does that mean? That means the phase of 1 over s squared, we can look at it, of course, as just minus 180, okay? But more importantly, you can see it as minus 90 degrees multiplied by 2, okay? Now, in general, we have that the phase of A plus B, or A times B, sorry, my mistake, will be equal to the phase of A plus the phase of B. And we'll see, for example, this is the case for the phase of minus J times J plus 1. Okay? The phase of minus J plus 1 will be minus 90 degrees plus, well, J plus 1 has a phase of 45 degrees. Okay? And so it is minus 45 degrees. And now we can check that by computing this number, which is 1 minus J. Okay? And indeed, the phase of 1 minus J is minus 45 degrees. What that means that we can, for example, and we will see that later, if we need to compute the phase of H times G of J omega, we will just need to compute the phase of H plus the phase of G, okay? And we'll get the right number. Now, let's talk about magnitudes for a second, okay, before we go any further. And so for magnitudes, how do things work? Well, almost the same way. If we take the magnitude of, say, a function h squared, it just turns out to be the magnitude of h squared. Now express it in decibels, and we get that 20 log in base 10 of h squared is simply equal to 2 times 20 log in base 10 of h. Okay, now that is equal to 2 times h expressed in decibels. Okay, and so what happens is that, for example, for a function like 1 over s squared, we can very quickly plot the phase and the magnitude of h, because we know that it's just going to be here just twice what it is, and there it would be also twice what it is. Okay, and so what we will get is the following. If I change color, okay, let me use some more convincing color like this. Okay, if this is h, such is going to be h squared. Okay, it's a line which is twice as steep as the previous one, that goes through the same crossover frequency here, and since the slope is twice as much, its magnitude is -2. Likewise, for the phase will be twice as much as the phase of 1 over j omega. In other terms, what we get is a phase of -180 degrees. All sorts of things that, of course, we could have guessed directly from here. But the ability to combine body plots of different transfer functions to obtain body plots of more complicated transfer functions is the key to why people like those body plots. Okay, and just to finish, we could talk, for example, about a transfer function which is again h times g. Okay, And the magnitude of these two guys in decibels, I'll let you compute that, will happen to be the magnitude of H expressed in decibels plus the magnitude of G in decibels. In other terms, when you take the product of two different transfer functions, the body plot of that product is just the sum of their body plots when we expressed H in decibels and omega in decibels or on a logarithmic scale. So that gives us, of course, a few more tricks, okay, to get these things. However, before we do these tricks, I would like to go over more simple transfer functions. The reason is because I mean they are sort of what I would call the building blocks. The building blocks for those transfer functions. Okay, so one of them is we have seen already constant numbers. Okay, we have seen 1 over s. Okay, of course, one thing would be, oh, we have seen 1 over s squared. The next thing we would like is k over s squared, where k is a number, or k over s to begin with. Okay, so again, now we can use what I said before, which is that the magnitude of k over s will be expressed in dB, will be the magnitude of k in decibels plus the magnitude of 1 over s expressed in decibels. Okay, so what does that do? Oh, and by the way, before I do more, the phase of k over s will be equal to the phase of k plus the phase of 1 over s. Okay, so what does that mean? That means as far as our plots are concerned, I'm going to plot the magnitude here, I'm going to plot the phase there. I'll assume k is greater than 0 to make things simple first, in which case if I use my omega axis here, and I assume my omega axis is logarithmic, and I plot whatever here in dB, okay, and here my phase, okay, then first of all, if k is greater than 0, then the phase of k is 0. That phase is still minus 90 degrees, okay. And magnitude-wise, well, here's what happens. First, I plot 1 over s in decibels. I've seen that before. We know it's a -1 slope when things are expressed in decibels here, and it crosses the 0 dB line at 1 radians per second, which is 0 dB radians per second, okay? So it crosses when omega is equal to 1 radians per second. Okay? Now the phase is minus 90 degrees. Okay? Now if I want instead the magnitude of k over s, well, what I need to do is just move this guy up or down by k expressed in decibels. So for example, if k is equal to 10, all I need to do is move this plot up by 20 dBs. And the plot of k over s will simply be this, okay? It will simply be a line with a -1 slope, which is lifted up by 20 dBs, and now it will cross at omega is equal to 10 radians per second. Okay? Now, I can do the same thing the other way around. If k is equal to 0.1, then that is minus 20 decibels. And so what I do is I take that same curve, I shift it down by minus 20 dB, and then I obtain the new plot, the new body plot here, which is down here. Okay, and now the crossover frequency is 0.1 radians per second. but otherwise the slope remains -1. Now phase-wise, things don't change. Okay. However, if, for example, k was equal instead to -0.1, what would happen? Well, what would happen is that my phase would be necessarily, instead of remaining at -9 degrees, it would be -90 degrees plus the phase of -0.1, which is 180 degrees. Okay, so it could be represented either as minus 270 degrees here, okay, or at plus 90 degrees, because 270 degrees is the same as 90 degrees modulo one wraparound. Okay, so that allows us to construct things like this. Okay, now in general, if we have the body plot of any transfer function, okay, so suppose our h, let me go back to a regular color. If we have our h like some transfer function, okay, I'm going to plot some random transfer function. So here is my magnitude, here is my phase, okay, and let's say my h does something like this, okay, which is a very inappropriate drawing, but that's okay. Then all that we need, if we multiply h by k to obtain k times h, is just shift this thing up or down by the size of k expressed in dB. So the amount here is k expressed in decibels. Okay. So when k is greater than 1, that moves the curve up, but otherwise keeps the shape the same. When k is less than 1, then it moves the curve down, but otherwise doesn't change the shape. And for the phase, the story is the same. Okay, so the phase is the phase of the original phase of the transfer function. Okay, shifted by whatever is the phase of k, which is 0 if k is positive, but which is 180 degrees if k is negative. So now let's look at specific functions h, okay, that carry some useful information and that can sort of help us in the long run. So one of the useful functions h is h is equal to 1 over s over a plus 1. We will see that this kind of first order transfer function is very useful. We can also rewrite it as, if we want, a over s plus a. It is the same thing. Now, what does happen? Well, in order to get the magnitude of h, we first write h of j omega is equal to 1 over j omega divided by a plus 1. And so what we can do in order to get a plot of this guy is, first we can go through complicated manipulations to get h of j omega. For example, you can say, well, h of j omega to get the gain would be simply the square root of 1 over omega squared divided by a squared plus 1. Oh, by the way, I assume a is greater than 0, okay, to make matters simple. And I mean, that would be one way to go, okay, but it's kind of painful and carries very little insight, okay. But before I go on for more simple considerations, so the phase of h would of course be the phase of, and I multiply by the complex conjugate here, I would get minus j omega divided by a plus 1 divided by j omega over a plus 1 times minus j omega over a plus 1, okay? And that would be the phase of minus j omega over a plus 1 divided by 1 plus omega squared over a squared. Now, since this guy is just a positive number, the phase will be the phase of this guy. And again, we can get some insight about things by computing this phase, but it might be easier just to go back to this guy and do some simple observations that s over a plus 1, j omega, we can compare j omega over a and 1. Why do we do that? Well, we don't even need the j here. What that means is that we're comparing how big this guy is. That guy is the imaginary part of this number versus 1. Okay? And what we see is that when omega is much less than a, okay, this guy really starts looking like 1 over 1. Okay? And of course, the magnitude of this guy and the phase of this guy are very easy to get. The magnitude is 0 dB and the phase is 0. Okay. Now, what happens when omega is much greater than a? Okay. Then we can say that then h of j omega really looks like as if the 1 here became a negligible term, and this becomes 1 over j omega divided by a, which is also a over j omega, or minus a times j divided by omega. Okay, and so, of course, once again, we can compute the magnitude of this guy fairly easily. We have done it a few minutes ago. And we can certainly compute the phase of this guy very easily as well. I can do that right away. And how would that go? That would go as follows. Okay, so let me clean up this area here altogether. And I'm going to use it to make my Bode plots. Since my and let me also move this guy out, because I think we could do that. Yes, we could do this as well. Okay, make some room, and now we have room for a Bode plot. Okay, so how does our Bode plot work? Well, what we're going to do is we're going to pick the magnitude plot. Again, magnitude in dB versus omega, where omega follows a linear scale, a logarithmic scale, and we'll do the same for phase. Suppose A happens to be here. Okay. So here's what we do. Okay, we get the idea that at low frequencies, for omega is less than A, oh, the gain is 1. Okay, and the phase is 0. So that means that our transfer function is probably not too far away from being a horizontal line, okay, which is right on the 0 dB line, okay, on that omega axis. Okay, now for the phase, we know that the phase is also on the 0 line. Okay, because the phase is 0. Okay, and again, let me point out A at about the same location, but for phase instead. Okay, and that is a 0 here. Now we know that past A, okay, when omega is greater than A, the magnitude looks like, well, literally A over omega. So what's A over omega? Okay, it is a line that goes through A, because when omega is equal to a, the magnitude is 1. Okay, so it goes through this point, and since it is 1 over omega, okay, it has a -1 slope. Okay, so here's what it looks like. Okay, it's like a line that goes through that point and then eventually becomes actually a line with a -1 slope here. Okay, now for the phase, this is a phase of -90 degrees. So again, past a, for higher values of omega, we know the phase is going to be about -90 degrees. Okay, which is about here. Now what can we do? Well, we say we have the phase and gain for high and low values of omega. Okay, one possibility is to do just linking the two lines and say, okay, well, this line I'm going to extrapolate this way, that line I'm going to extrapolate this way, and then they're going to meet here at what's called the breakpoint. Okay, and likewise here we can say, okay, the phase is 0, and then it jumps down to -90 degrees. Okay, and that would be actually a not so bad linear approximation of the true transfer function, because the true transfer function is actually something like this, but a smoother version of it. Okay, so what it does is that it actually follows the behavior I mentioned before. Okay, but here, instead of making a sharp corner when it switches from the horizontal mode to the -1 slope mode, instead it does that transmission smoothly. And the same is true for the phase. Okay, the phase transition is actually much smoother than just a brutal step down of 90 degrees. Okay, now let's see that in a Bode plot for an actual system. Let's pick as our system 1 divided by s over 10 plus 1. And let's see what the phase actually looks like. So for that, first I erase my first thing, and then I redefine my system. So again, I use that trick about changing magnitudes for omega in such a way that we can read the numbers on the horizontal axis as if they were in radians per second. I define h now is equal to 1 divided by s divided by 10 plus 1. Okay, so again, that introduces a change in what we define by s divided by 10, but we don't pay too much. We try not to pay attention to that. And then, by the way, I've disappeared. Let's see if I can fix that. Okay, there I am. There I am back. Okay. So what we do is we do Bode of, we first define our system. Okay, cis equal cisln of continuous h, and then we do Bode of h, of cis, sorry. Okay, so the Bode plot that we use, because we did the change of s, okay, so that Bode plot is going to come, okay, let me erase this and let me redraw it. So because of the change I've done on s, remember I've divided it by 2 pi, we get the following, okay. We actually can read the horizontal axis as if they were radians, not hertz. Okay. Now again, for those of you who use MATLAB, you don't have this problem. And then you can read indeed the magnitude and the phase. And what you see is that the phase starts indeed at 0 degrees at high frequencies above 10 radians per second. Okay, the phase is close to -90 degrees. And then around 10 radians per second, it transitions smoothly from 0 to -90 degrees. Okay. Now, the actual approximation of this guy, if we were to put it in the okay, so let's see if we can do that. What I'm going to do is I'm going to take this guy and then try to see if I can put it in my environment here. Okay, yes, I can put it in my plotting environment so that the approximation of my my gain, okay, that I would have done with the help of my rule, okay, would have been to say this guy goes horizontal up until 10, and that makes a sharp turn, and it meets this guy, okay, which is the line of slope -1, which approximate that actual line here, okay, -1 because for 20 dBs of jump here, we move forward 20 dBs there, okay, and likewise for the phase, we could do the same approximation, okay, and the approximation would have given us that the phase stays at 0 degrees, and then at 10 radians per second, it violently jumps down 90 degrees, okay. So of course you see that there is some difference, okay, and one useful thing is to compute the difference here, okay, between these two guys. Okay, how does that go? Well, on the one hand, what you're comparing is the value of the transfer function at 10 radians per second. This is going to be 1 over j plus 1. Okay, that's at, so that's h of j omega when omega is equal to 10 radians per second. And then the value here at a is 1. Okay, the value of my linear approximation here, my piecewise linear approximation, is 1, right? Because it is 0 decibels. Okay, so if we want to compare the difference between this and this guy, what we can do is compute the magnitude of this guy, which is 1 over square root of 2, and compare it with 1. Now, square root of, and the ratio of these two, okay, that is the distance between these two, is square root of 2, okay? Now, in radians per second, in decibels, square root of 2 in decibels is 3 dB, okay? Why is that? Because the 2 expressed in decibels is 6 decibels, okay? So square root 2 is 2 to the power 1/2, and so the magnitude in dB is 1/2 of the size of 2 in decibels. All right. Now, what that means is that the difference here between these two guys is exactly 3 decibels. Now, why is that useful? Well, because it allows you to sort of take that linear approximation here, that linear approximation there, take the corner, drop it 3 dBs, and now you have one more point which you know lies exactly on this curve for, again, that transfer function, which is 1 over s over 10 plus 1. I'll let you extrapolate to anything like 1 over s over a plus 1. Just replace this guy by a instead. Okay, and the story is exactly the same. The breakpoint lies 3 dBs above the actual value of the gain here. Okay, so for the phase, again, you have a certain number of rules, and you can follow them. You will see them on in the book, and they tell you like how much actually the approximation of the phase, which is the step approximation, how different it is from this sort of smooth phase thing here. Okay. All right. So now what we can do is go back to our drawing board and look at other kind of useful transfer functions. We now have 1 over s, we have 1 over s squared, we have 1 over s over a plus 1, okay? So, of course, we have 1 over s plus a, because this is just equal to a over 1 over, sorry, S over A plus 1. Am I correct? No. This is 1 over A times this guy. But since we have this guy expressed, we can plot the transfer function of this guy over the body plot of this guy. We can certainly plot this guy times that, since this is a positive number. It's just a scaling factor. So we can plot, by the way, any k over S over A plus 1 as well. Okay. Now notice that if we have this, we can also plot the body plot of 1 over S times 1 over S over A plus 1. Why? Because we can use the rules that this expressed in dB will simply be equal to 1 over S expressed in decibels plus 1 over S over A plus 1 in decibels. And that we already have. Okay? And phase-wise, the story is the same. So let's spend a little bit more time looking at this and see what happens. Okay? So I'm going to pick, for the sake of the example, A is equal to 10. Then I can plot my gain here. Okay, I will use this value here. Okay, that is omega. I will say that omega is equal to 1 is here, and omega is equal to 10 is here. Okay, these are particularly useful things, okay, to remember. Now, my phase, I will plot here. So here is my gain in decibels, and here's my phase in degrees. Okay. Now let me look at 1 over S first. So we know the plot for 1 over S. It is a plot which goes through 1 and which otherwise is a linear plot with a -1 slope. Okay. In other terms, when I cross the 10 radians per second here, I have gone down 20 dBs. Okay. Now, what I'm going to do is I'm going to make a little room and move this guy a little bit because I need some room. There is always the recurrent problem of not being able to show gain over the proper scale at the beginning. Okay, so that's one of, oopsie, sorry. So that is 1 over S, okay, as it keeps going, okay, with that -1 slope. Now 1 over S over A plus 1, what is that? Well, we know that it is more or less a horizontal line which goes like this, okay, and then breaks off with a -1 slope here. Okay, once it passes 10 radians per second. Okay, now for the phase, the story is about the same. Okay, the story is that the phase of 1 over S is -90 degrees, and the phase of this guy starts at 0, but at 10 radians per second, which I forgot to point out. Okay, so this is 10 radians per second. This is still omega. Okay, and this is still 1 radians per second. Okay, the phase drops, okay, to get to -90 degrees. So if you have the product of these two transfer functions whose body plot we want to plot, it is very simple. We take the magnitude plot of 1 over S, we take the magnitude plot of 1 over S over A plus 1, and we add them up. So what does that mean? That means that up until about 10 radians per second, the sum of these two is just the red thing. Okay? Because the orange thing is at 0 decibels. And then once we arrive at the characteristic frequency here of 10 radians per second, okay, so when, and again this corresponds to A is equal to 10, okay, so the break frequency, what we do is we add these two lines. But when you add these two lines, what does that mean? That has the same effect as drawing a line of slope -2 instead, which starts at the same point as when this guy was going down, but then eventually breaks away with a slope of -2 instead of -1. Okay, so that is the frequency response of this transfer function. Okay, at least approximate. Then we can of course do the little smoothing as we have talked about before. For the phase-wise, the same story. The phase starts at -90 degrees, okay, and the vicinity of this, so since the phase add up, okay, the phase drops again by the same amount as that one drops off, and therefore what we find ourselves with is that the phase dropped to -180 degrees. Okay. Now, by the way, if you remember, this is the transfer function for a small motor. Okay, so we will be talking at length about how to change that transfer function to our liking later in this course. But now we know how to compute products of this transfer function and how to represent them as Bode plots. Okay, when we have the individual transfer functions. All right. So that is particularly useful, and again because it allows you to draw by hand all these transfer functions and arbitrarily complex transfer functions. So we can embark into other kind of transfer functions. When we have done that, why not do more complicated, right? One of the key transfer functions, of course, that we will use is what if h is equal to 1 plus s, or 1 plus s over a. So it's the opposite of the other, okay? Or it's the inverse, okay? Or h is equal to s, okay? So h of j omega, when h is equal to s, is just j omega. When h is equal to 1 plus s over a, okay, h of j omega is equal to 1 plus j omega over a. Now, these transfer functions, they behave the same way as the others, but they are the inverse of what we dealt with. So how does that work? Well, if you can think about it here, we need to again consider the case when omega is much smaller than a, in which case h is about equal to 1, okay, and omega is much greater than a, in which case h is approximately equal to j omega over a, okay, and that is actually 1 over j omega over a. My mistake. Yes, that's correct. Okay, 1 over j omega over a. Okay, so it's the inverse of a transfer function that we have already seen. Okay, now how does that work when we draw things? Okay, I can start beginning with this, okay, and then do that thing later. So for this guy, here is the gain and here is the phase. Okay, so the gain will be, again, we use decibels everywhere. Okay, and what we know is that this guy will be 1. Okay, so this is the 0 dB line. It will be 1 at omega is equal to 1 radians per second. And then otherwise, what will it be? Well, it's growing linearly with omega. So instead of the -1 slope that we have seen before, okay, the value of h plotted in decibels against omega, which is plotted against in decibel, will be a slope, a line, but instead of a slope -1, it will be a slope equal to +1. Okay, and that's normal because j omega is 1 over j omega. Okay, and what happens is that when we plot this in the decibels, what we get is a reflection across the omega axis. So if you remember what we had, so this is h of j omega, okay? And if we plot instead 1 over j omega, okay, what we get is that line instead, okay? So it's the line that crosses the other one, but with slope of -1. One is the inverse of the other, and that amounts to reflecting this line across the omega axis to become that line. Likewise for this guy, okay, this is 1 over 1 plus j omega over a, okay, but we can look at this and say, so if a is here, okay, then what is this guy? Well, I said it's about 1 magnitude-wise until it reaches a, and then it looks like j omega over a. And j omega over a is precisely the line of slope +1, okay, that this guy eventually espouses. Okay, now the true transfer function looks like this. Okay, it smooths out here, it takes the rotation, and that rotation is exactly the mirror image of the transfer function we had seen earlier in previous plots. Okay, which was 1 over s, 1 plus s over a. Okay, so that's 1 over 1 plus s over a, okay, which ends up with a -1 slope. Okay, so so what you see is that, first of all, now we have transfer functions with positive slopes, okay, for this guy and for that guy. And second, those transfer functions can be obtained from their little sisters, which were their inverses, okay, by just flipping the initial transfer function about the omega axis, both for this one and for that one. And of course, we now have enough tools to compute, for example, the transfer function of h of j omega is equal to s squared. Okay, the story is the same. It's going to be a positive line of positive slope plus 2. Okay, and phase-wise, we can actually recover all these phases as well. Okay, the phase of j omega will be again mirrored against 0 degrees from 1 over j omega, which is a phase of 90 degrees. Okay, whereas the other one that we did before, okay, for 1 over j omega was -90 degrees. And for this transfer function here, okay, 1 plus j omega over a, instead of having a transfer function phase which was doing pretty much like this, okay, that's what we saw last time, okay, and which crosses over at a here and matches this transfer function 1 over 1 plus s over a. What we do is we reflect this thing across the 0 degree axis, and instead we obtain that the phase goes up by 90 degrees. Okay, and so again, the game of the mirror images works as well. And then we can, of course, divide these transfer functions all together and obtain composite plots, okay, that are equally satisfactory. This ends this lecture. Thank you.